Welcome to the O-Level Chemistry Lecture Series. Today's topic is on metals. To begin with this lesson, please make sure you have ready on hand the notes, as the lesson will be delivered through PowerPoint, which will closely mirror the flow of the notes. These are some of the additional recommended practices. And here we have it, metals. So before we move on into the topic of metals, let's take a look at some metal items that we commonly encounter in our everyday lives. So I have here with me a metal bell. You should have seen this metal bell before in your, maybe at the shops, at the bubble tea shops. Over here, this is a aluminium tube xylophone. You would probably have seen this as well. And of course, this item here, which you would definitely have seen. This is your Catholic high school badge. So all these objects here are made of metals. I'm sure if you look around you, you will see many other objects which are made of metals. So some other common metals are as shown here. Brass. Brass is commonly used to make locks. Aluminium, used to make your aluminium foil. Cast iron, used to make engine blocks. Copper for wiring. Steel for steel beams in making your structures. Bronze for making sculptures, making statues. Metal sludge, mainly more for some of the industrial purposes. So let's have a quick recap of metals. They are mainly found in groups 1, 2, 3, and the D block. 1, 2, 3, if you recall, they are here. There are 3 parts to the periodic table. Group 1, Group 2 are here, Group 3 is here, and this is the D block. So why are metals found in Group 1, Group 2, and Group 3? It's because, if you recall, most of the metals have 1, 2, 3 valence electrons. So for example, if I have potassium, K has 1 valence electron, it loses that electron to form the K plus ion. Right? So having 1 valence electron places it in group 1. So as I just mentioned, metals tend to lose their valence electrons to form positive ions. So it's easier for potassium to lose its valence electron than to gain another electron, because it's always easier to lose something than to gain something, correct? So similarly for metals, it's easier for metals to lose their valence electrons to form positive ions. The structure of metals: giant metallic lattice, closely packed. So if you were to draw the lattice structure, it would be closely packed, closely packed, closely packed. And you have electrons, C of delocalized valence electrons. These are the cations. And the C of delocalized valence electrons. So this is the giant metallic lattice. One more thing about the valence electrons: because of this C of mobile valence electrons, when you apply a charge across a metal block, say we have positive and negative charge here, a potential difference. We apply a potential difference across a metal block. The electrons can migrate across the metal block, so this allows the metal block to conduct electricity. So we say metals can conduct electricity. So metals have some or all of the following physical properties: lustrous and sonorous. Just now you heard the xylophone. The sound is because metals are sonorous. High density is really heavy. It's really heavy and it can sink. So if you recall, density equals to mass over volume. So per unit volume, if I have a block of, say this is a block of iron, and a similar size block of wood, my metal block here, my iron block here would sink in water. It has a very high density. So why does it have a very high density? Because for every unit volume, there are a lot more particles packed into that volume compared to wood. So as a result, the mass is extremely high. So high mass, small volume, density will be high. Malleability. So malleability is a property by which the metal object can deform without breaking. So if I were to bend a metal ruler, the ruler will bend, the ruler will not break, So this is malleability. Ductility is the property of being able to be stretched into wires. So stretched into wires. Stretch into wires. So if I have a block of copper and it is heated to a sufficiently high temperature, I can actually grab this end and grab this end and pull, and I'll be able to stretch it out into a wire without the copper breaking. It has a high melting and boiling point. Why high? Because if you remember, the metallic bonds, the electrostatic forces of attraction, between the cations and the sea of valence electrons is very strong. So if it is very strong, it means that you need a large amount of energy to break these forces of attraction, and to supply this energy you need a large amount of heat. Hence it has a high melting and boiling point. They are good electrical and thermal conductors. The presence of the valence electrons, the delocalized valence electrons in the structure, they allow the flow of current. Through the block of metal. So this is the structure of a metal. You have your valence electrons, which are randomly dispersed. See your delocalized mobile valence electrons. Plus minus here, the electrons migrate over here. So as a result, the metal can conduct electricity. So similarly, to conduct thermal energy, if you recall, thermal energy is one of the main forms in which thermal energy is contained in a particle is through vibrations. So when the atom vibrates and it transmits the vibrations throughout the whole structure, this end becomes hot when we apply the heat on this end. So for metals, you have the mobile valence electrons which migrate rapidly. So the electrons can actually carry that energy. They move about very rapidly, and they carry this energy from one end to the other end really quickly. That's why metals are good thermal conductors. And last but not least, they have high tensile strength. Why high tensile strength? Because of the very strong electrostatic forces of attraction between the cations and the sea of the delocalized valence electrons. So before we move on into the structure of metals per se, let's talk about this thing which we call an alloy. You would have probably heard of alloys before. So alloys are used to make lots of materials. For example, duralumin. This is an alloy of aluminium, magnesium, and some other compounds, and this is used to make the bodies of aircraft because it is extremely strong. Steel, for example, steel is an alloy as well. Steel contains iron and carbon because by itself iron is a bit soft. So to strengthen the iron, we add in carbon, and this is called steel. So steel can be used to make knives such as the one shown here. You wouldn't want your edge to be blunt every time you cut vegetables. You will want to use your knife for quite a few instances first before you need to sharpen the knife. So in order to make sure that your knife remains sharp, we use steel, contains iron and carbon, strong. So a strong edge can be obtained. So why are alloys much stronger than the original metal? Because if you take a look at this diagram over here, you will see that the structure of the metal, this is the metal, and this is the added substance. So notice that the metal structure is disrupted. So in order for a metal to deform, the layer must slide. Correct? So this layer must slide. But in order for this layer to slide, there must not be anything here blocking the layers. So if I want to slide this layer over here, I will find that it is pretty difficult. Why? Because it has been obstructed by two other foreign particles. So in essence, when I alloy something, I add small amounts of metals or other non-metals, and this different sized atoms of other metals or non-metals disrupt the regular orderly arrangement of the metal atoms. It disrupts the regular orderly arrangement, and thus the layers cannot slide over each other, and as a result the strength of the alloy is much higher than that of the original metal. Okay, so now we move on to this very interesting series which we call the reactivity series of metals. So this series here basically tells us how readily a metal reacts to form positive ions. So at the top we have potassium, at the bottom we have gold. This series does not contain every single metal, because if it does, you would probably be memorizing the series all day long, not learning any real things. So we have a selection of metals in this series. Potassium at the top being the most reactive metal in the series. So by reactive, it means that it has the greatest tendency to lose electrons to form positive ions. So K becomes K plus E minus. So this has the greatest tendency to form K plus. Over at the bottom, gold, Au, this is the least reactive metal. This is the least reactive metal. So this has the least tendency to lose electrons to form positive ions. So if I were to say it in a different way, I can say that this metal is the most reactive and hence the least stable. Gold would be the least reactive and hence the most stable. Which means when my potassium metal, which is the most reactive and least stable, forms the K plus ion, the K plus ion is more stable than the metal. Conversely, for gold, if gold was to form an ion, the ion would be much less stable than the original gold element. So we use the reactivity series to predict what chemical reactions will take place. For example, if you know that copper does not react with dilute hydrochloric acid, if copper does not react with dilute hydrochloric acid, no reaction with dilute HCl, based on the series, do you think that mercury would react with dilute HCl? No. So it wouldn't react as well, because at the bottom of the series is the least reactive metal. As you go downwards, it becomes more and more unreactive. So if copper doesn't react with dilute HCl, it means that mercury, silver, and gold will not react with dilute HCl. Right? So this is how the reactivity series is used. It will be used later in the topic of electrolysis as well, to help explain what ions are preferentially discharged at the electrodes. So we move on to the chemical reactions proper. There are 9 main reactions, there are 9 main area of reactions which we will need to learn. So you can see here there are 9 main reactions, but in fact, most of them here are very similar. So these two parts have very similar reactions ongoing. This one is actually really easy. These two parts are related, and this one is a simple redox reaction in progress. So let's move on to the first part, the reaction of the metals with water. So maybe before we go into the long and boring equations which you will need to know, let's watch a quick video on some of the reactions of these metals here with water. We can't show all the metals here though. Only the group 1 metals are shown. Most of the group 1 metals are not in the reactivity series, but for those which are in potassium, sodium, the video will show how they react with water. The following video is by Brainiac. It is obtained from YouTube. So it describes how the group 1 metals react with water. Some of them which are extremely reactive show very explosive reactions. So let's all take a look.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water.
So this one shows a lithium water reaction,
I've mixed H2O with
a sodium water reaction. You see a small flame here.
very strict scientific control have witnessed potassium mixed with water.
Potassium in water, you notice the metal spontaneously combusts when it's in water.
If you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkaline metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium. Here it is.
This is rubidium.
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety. Right, so what's going to happen when you drop that in the water? Well, imagine, if you will, letting off a hand grenade in a bathtub. Righto, I'm off. Have that. Okay, good luck. Okay, Tickle. Drop the rubidium in the water.
The rubidium is being placed in the water now.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
So as you can see, the reaction between metals and water can be pretty violent and pretty reactive. Alright, so the table here describes the different reactions of the metals with water. You notice as the metals go down the reactivity series, the intensity of the reaction actually decreases. This is extremely violent reaction, violently, radially, slowly, does not react. So once you know that something does not react with cold water, all the metals below it in the series will also not react with cold water. Lead, copper and silver especially will not react with cold water or steam. So steam is hot water vapor. Okay, so the chemical equation is actually quite standard. The metal plus water will give you the KOH and hydrogen gas. Notice this is the hydroxide. Later on, when there's a reaction between the metal and steam, you will get the oxide. Whenever there's water present, you will get the hydroxide or the hydrated oxide. So very easy to remember. When there's water, you will get the hydrated oxide. When there's no water, when there's steam, you will get the oxide. All the reactions are the same. You notice it's just the hydroxide with hydrogen gas. Same. This one is particularly interesting. Is Fe3O4. Take note, it is not Fe2O3. It's Fe3O4. Okay. This is iron 2,3 tetroxide. This is iron 2,3 oxide, or called tri-iron tetroxide. So if we go into the reactivities of the metals one by one, sometimes you'll be asked to describe what happens. These are the few keywords you will need to write out. So potassium, you must say it reacts very violently. The very is important with cold water. A lot of heat is produced. You have hydrogen gas. You have heat and hydrogen gas. Then you have the explosion. Kaboom! It catches fire and explodes. The metal burns with a lilac color flame. Lilac, something like purple color. And these are the products formed. And if you expect that the metal reacts very violently with cold water, if you put in hot water or you use steam, there will be a very violent explosion. So this is a deduction that we can draw based on the reactivity of the metal with cold water. Okay. Sodium is the same. Violently, H2 produced, catches fire. Yellow color flame. Products are the same, hydroxide and hydrogen gas, and it will explode with steam because it reacts very violently with water. Calcium is starting to decrease in intensity of reaction already. This reacts radially with cold water. The metal sinks. Why does the metal sink in this case? And the first two cases not mentioned. The first two cases, if you recall, group 1 metals are very light. They are less dense than water, so they will actually float. For calcium, it sinks. When it reacts, it produces hydrogen gas. But this case, notice that there's not much heat produced, so the gas doesn't catch fire and can be collected over a test tube here. We get the hydroxide and we have hydrogen gas, and after some time you notice the water turning milky because calcium hydroxide here, if you recall, this is lime water. So CaOH bracket 2 calcium hydroxide is actually not very soluble in water, so you only dissolve a little bit of calcium hydroxide into water to give you lime water. Any more and you will have a milky whitish color solution. Magnesium reacts slowly with cold water. Notice from readily is now slowly. We are going down the series now. Potassium, sodium, calcium, magnesium. So magnesium is one below calcium. Only a few bubbles of H2 gas are produced. We have the same hydroxide and hydrogen gas. But when we heat up magnesium, when it is hot, there's sufficient energy for the reaction to proceed really quickly. It reacts violently with steam. Steam is hot as well. H2O, it is hot as well. So both magnesium and steam are hot. The reaction will proceed very quickly, and we have magnesium oxide, not the hydroxide. Recall just now when I said only when it reacts with water, liquid water, then will you get the hydrated oxide, which is hydroxide. When it reacts with steam, we have the oxide, solid state, and we have hydrogen gas. We have a bright white glow. So if you have seen fireworks before and you have seen white color fireworks before, the white color of the fireworks, if the fireworks are white in color, the color comes from the burning of magnesium. Zinc is one step below aluminium, so it's magnesium, aluminium, zinc. So potassium at the top. So zinc does not react with cold water. So all the metals below zinc will not react with cold water, but zinc reacts readily with steam, hot zinc with steam, and this is important. It is white when hot, yellow when hot, and white when cold. So zinc oxide here is yellow when hot, important, and white when cold. So why is this observation important? Because sometimes the questions will ask you and they will say XYZ, something reacts with something, and the product is yellow when hot and white when cold. So what could the product be? So having this knowledge of zinc oxide being yellow when hot and white when cold, you will be able to deduce straight away that the compound that is formed could be zinc oxide. Okay? Iron does not react with cold water, it's below zinc, but red hot iron reacts, but slowly with steam to form your iron 2,3 oxide, or your tri-iron tetroxide here. Lead, copper, silver, no reaction with cold water or steam, no reaction. They are unreactive metals, they are considered relatively unreactive, so they do not react with cold water or steam. Now I have a question for you. So aluminium is above iron and zinc in the reactivity series. So if I write the series out, it is potassium, sodium, calcium, magnesium, aluminium, zinc, iron. Aluminium is in fact above zinc and iron, but aluminium actually reacts very slowly, and we use aluminium to make a lot of things. For example, aluminium saucepans, aluminium car bodies, aluminium poles, aluminium tent packs. Why do we still use aluminium when it is more reactive than zinc? So why does aluminium react slower than iron and zinc? Why? This is because being a highly reactive metal, let me erase this part first. So being a highly reactive metal, the aluminium in fact can react with the oxygen in air. It reacts with oxygen in air, Al plus O2 in air, to give you Al2O3. So this is a balanced equation. So this aluminium oxide layer is impervious to air and water. Impervious means that no air and water can get through. So if this is aluminium block and this is the Al2O3, if I have water and your oxygen, they will not be able to enter for further reaction to take place. So no oxygen can touch the aluminum metal. So in essence, this aluminum oxide layer actually forms a protective layer around the aluminium block. So if we want the aluminium block below to react quickly, we must first remove this oxide with some acid, because the oxide is a metal oxide. So a metal oxide is a basic oxide. So basic oxide you can react with H plus or acid to give you a salt and water, right? So just now we covered the reaction of the metals with water. We now move on to the reaction of the metals with hot air. With hot air. So what is the main thing in hot air which reacts? It is actually oxygen. So if you take a look down the series, you only need to apply some heat for potassium because it is really reactive and you get a very, very vigorous reaction. So K plus O2 gives you K2O, potassium oxide. As you go down the series, the intensity of the reaction decreases. You need more heat to start the reaction. Eventually, when you reach gold and silver, no reaction takes place. So let's go through this one by one. Potassium, what are the key points you need to write? Apply some heat, very vigorous reaction. During the reaction, once the reaction has started, a lot of heat is given out. The metal burns with a lilac flame and we get a white powder of potassium oxide. For sodium, only some heat needs to be applied. Same thing, you get a vigorous reaction. A lot of heat is released. It burns with a yellow flame and we get white color sodium oxide powder. Notice that the oxides, the color of the oxides of group 1 metals are always white in color. Okay, group 1 metals are always white in color. So whatever group 1 metal, it will be white in color. Calcium, magnesium, zinc, you need to apply strong heat because they are less reactive. There's a lower tendency for them to give up their electrons. You must apply more heat to start the reaction off. But once the reaction starts, a large amount of heat is released. You again get white solids produced. So group 2 oxides are also white in color. And if you recall from earlier, magnesium burns with a white color flame. Iron, same thing, strong heat to start the reaction. When the reaction starts and continues, it glows red hot. And if it is really, really intense, a lot of heat is produced. You see the iron burning with white sparks. So over here, you see the iron glowing red hot. Why? Because the iron is undergoing the reaction with oxygen to form your iron 2,3 oxide or iron tetroxide. Lead, copper, you must apply strong heat to start the reaction. There's no vigorous observations because it is relatively unreactive. And like all the other more reactive metals, you get the oxide form. Copper oxide, lead oxide, KPbO and CuO. Copper oxide is what color? If you recall, this is black in color. So this is a distinguishing color for CuO. Questions you ask, what is the black substance that is formed? You must deduce that it could be CuO. For gold, silver, no reaction, nothing happens because they are very unreactive metals. We move on to the next part here, the displacement of metals or metal ions by a more reactive metal. So if you observe in these two beakers here, on the one on the left side, you have a silver piece of zinc that is dipped into copper 2 sulfate, aqueous copper 2 sulfate solution. On the right side, you have the same piece of zinc. This is the same piece of zinc. But now, you notice at the bottom here, it is coated with a layer of substance. So, what is this substance? This is actually copper. So, where did the copper come from? There's only one place where the copper could have come from, and that is the copper sulfate, Cu2+. So, Cu2+ must have reacted with copper. Cu2+ must have reacted with zinc to give you Cu, solid. Then what about the zinc? Where did the zinc go? So if copper 2+ forms copper, this is a reduction reaction. 2 plus 0 is a reduction, which means that the zinc must be oxidized. If the zinc is oxidized, what does it form? It forms zinc 2+. And because this is a aqueous ion, it enters into the solution. So after some time, your zinc block here will actually start dissolving and the mass will decrease. And you notice one more observation here. This is actually quite an intense blue color. The blue color comes from Cu2+ ions in water. After some time, when the Cu2+ has been deposited as copper, you notice that the color here is actually less blue because the concentration of Cu2+ ions has decreased. So this equation here sums up the displacement reaction. We say that zinc has displaced copper 2+ from copper sulfate to give you zinc sulfate and copper metal. So as I described earlier, when you dip in the piece of zinc it becomes coated with a layer of copper. So copper is sometimes called brown, sometimes they will call it pink, sometimes they will call it reddish brown, but you need to know these are some of the colors which questions have been using to describe copper. So as the reaction proceeds, the blue color solution slowly fades in color. Eventually, when all the copper 2 plus, has been displaced as copper, it means that there will be no more Cu2 plus left. So it means that because there's no more Cu2 plus and the blue color solution is from the Cu2 plus, the solution will become colorless. Okay, so this only takes place if the zinc metal is held in there for a very long period of time and the copper at the bottom here is continuously scraped off to expose more zinc for the reaction to take place. Right, so now why does zinc displace copper 2 plus from the copper 2 sulfate solution? A very simple explanation for this is because zinc is higher up the reactivity series compared to copper. So we can say that the more reactive metal, take note of this, more reactive metal displaces the ion of the less reactive metal from solution. Take note, I've used the word metal displaces the ion of the less reactive metal. It's not the metal displacing the metal. Cu2 plus is displaced by zinc to give you zinc 2 plus copper metal. So it is the metal which displaces the ion from aqueous solution. So if I were to change the question a little bit and I would ask you, can I dip magnesium into a solution of copper 2 sulfate and I have my copper 2 plus displaced? The answer would be yes, because magnesium is more reactive than zinc. So if Mg were to be dipped in copper 2 plus solution, I will similarly have Mg2 plus Cu solid metal. So what happens during the displacement reaction? The zinc dissolves, gives you zinc 2 plus. This is an oxidation reaction. It loses 2 electrons. Where do the electrons go to? The copper 2 plus becomes copper 0. So it must gain 2 electrons. So the electrons are transferred from zinc to copper 2 plus. So this is a reduction reaction. So together, this is a redox reaction. An oxidation has taken place and a reduction has taken place. So this is another example of a simple displacement reaction involving solid substances. So earlier we used aqueous solutions. Aqueous solutions and displacement has occurred. You would have heard before that reaction between solids is not possible. However, if we provide enough heat to start off the reactions between solids is actually possible. So if you look at this equation here, zinc solid and copper oxide solid, zinc is actually more reactive than copper 2 plus, than copper. So zinc will be able to displace copper 2 plus from copper 2 oxide to give you zinc oxide and copper solid. We just need a heat source to start off this reaction. Right? So the magnesium ribbon is ignited. So when it is ignited, it produces a lot of energy. If you recall earlier, magnesium burns in oxygen, bright white flame, very hot. It gives you white color magnesium oxide. So this heat is used to start the reaction. And when the reaction starts, it is extremely vigorous. So it is self-sustaining because there's enough heat produced to sustain the reaction. And we have a lot of heat and light given off during this reaction. The reaction sustains itself until eventually there is no more copper oxide left or no more zinc left, and then the reaction will stop. Okay, so what do we have at the end of the day? We have the zinc displacing the copper from copper 2 oxide. Okay, so this table here actually shows the displacement reactions for some metals and some metal cation ions. You will need to be able to describe what are the color changes. For example, if I were to say you were to dip a piece of magnesium into zinc sulfate solution, what would you observe? You must tell me that magnesium is more reactive than zinc, so we can displace zinc 2 plus from solution. As a result, you get the gray deposit of zinc on magnesium, and the solution remains colorless. So if I were to put in zinc into copper 2 plus, you will have the copper being deposited, and after some time the solution fading in color and then becoming colorless. So take note, all the color changes here, all the colors All the color changes here are very important. And this table here summarizes some of the reactions we've just gone through. The first one is the appearance of metals. This one was covered in the earlier topics of chemical bonding. This is the reaction of water with the metals. So as you notice, as it goes down the series, it reacts with decreasing ease. Decreasing ease as it goes down. Eventually, when it hits the bottom, there's no reaction with steam or water. Acid metal reactions we have learned before already. You will have a acid with metal. So acid with metal, you get salt and hydrogen gas. So the more reactive metal react with more vigorous intensity. You get a greater amount of effervescence occurring. You have it occurring in a faster period of time, and possibly it could be explosive as well. So imagine if I put potassium into water and it explodes, potassium into acid, it would be a even more violent explosion because there's water present and there's H plus present. Two different things can react with the metal now, so it's a double whammy, very explosive reaction. As you go down the reaction, as you go down the series, notice that it does not react with the acids. So copper, Hg, copper, mercury, and silver here, oxidizing acids, they only react with HNO3. HNO3. Copper does not react with hydrochloric acid. It does not react with dilute sulfuric acid as well. Okay, copper does not react with dilute acids. Burning wise, the metal burns in oxygen in air to give you the metal oxide. At the bottom, unreacted, unaffected because they are very unreactive. Displacement reaction wise, the metal above can displace the cation of the metal below from the solution of its salts. I mean, it displaces it from its aqueous solution. So now we move on to checkpoint 1 to have a quick recap of the different concepts and different equations learned. So pause the video now to attempt the checkpoint. Continue the video once you are done. In checkpoint 1, we have zinc powder added into a solution of copper 2 sulfate. So if you remember, copper 2 sulfate aqueous solution is blue in color. So zinc powder is placed to copper 2 sulfate solution. After some time, you get a colorless solution and reddish brown solid forming. So what is this reddish brown solid? Write the chemical equation for this reaction and the ionic equation for this reaction. So zinc into copper 2 sulfate solution. First thing we analyze this question, zinc, we must think of it of its position in the reactivity series. Zinc is above copper in the series, so zinc is on top, copper is below. So because zinc is above copper in its reactivity series, zinc will be able to displace the copper ion from its aqueous solution. So we can deduce that the colorless solution is because zinc has displaced all the Cu2 plus from the solution, and the reddish brown solid would be the copper that is formed. So this is the overall chemical equation. Zinc plus copper sulfate gives you zinc sulfate plus copper solid, and the ionic equation for this would be zinc plus Cu2 plus gives you zinc 2 plus plus copper. If you forgot how to derive the ionic equation, let's go through this in a little bit. So we have zinc solid plus copper sulfate, Aq, giving us zinc sulfate, Aq, and copper solid. So the ionic equation tells us what ions are involved in the reaction. So the rest of the ions which are not involved, they are called spectator ions. So because it's an ion based equation, we must first know which compounds here can dissociate to give you ions in aqueous solution. So if we write this down, zinc solid will be zinc solid, it can't dissociate. Copper sulfate on the other hand can dissociate to give you Cu2 plus Aq plus SO4 2 minus Aq. Zinc sulfate Aq can dissociate to give you zinc 2 plus Aq plus sulfate Aq, and copper solid remains as copper solid. So what ions are present on both the left and right side of the equation? It is the sulfate ion, and we can cancel these two ions out because they do not participate in the reaction. So if it starts off with SO4 2 minus and it ends off with SO4 2 minus, it means that there has been no change to the SO4 2 minus, so it remains the same, unchanged. So what we have left are the ions or elements which clearly take part in the chemical reaction. So if we rewrite this equation out now, we will have Zn solid plus Cu2 plus giving us Zn2 plus and sealed. So there we have it. We have the ionic equation. So very simple. Step 1, write equation. Step 2, dissociate whatever you can dissociate into ions. Step 3, cancel all the ions that are the same on the left and right side. And step 4, rewrite the equation. And this is your ionic equation. So zinc displaces copper 2 plus from solution to give you zinc 2 plus plus copper solid. Right? And we have this equation here. The next part of the question involves you writing a few more chemical equations, if any, when you add the metal into the aqueous solution. So zinc and aqueous silver nitrate. Zinc, we know it's above silver in the reactivity series, so yes, there will be a reaction which will take place. Copper and silver nitrate, we know that copper is above silver in the reactivity series as well, so yes, a reaction will take place. We get the copper 2 plus and we get the silver metal. Zinc into aqueous sodium chloride. We know that zinc is below sodium in the reactivity series, so will there be a reaction? No, there's no reaction which will take place because zinc is less reactive than sodium, so it cannot displace the sodium ion from an aqueous solution. Part 3, thermite reaction. So the thermite reaction is a very common reaction used to produce molten iron to weld railway lines. So during this reaction, a large amount of heat is released, and there's actually no need to melt the iron to weld the railway lines because the iron that is produced in the thermite reaction is molten iron. So it involves the reaction between aluminium powder and powdered iron 3 oxide, Fe2O3. When these two are added together, a lot of heat is produced, okay, and aluminium, being higher in the reactivity series than iron, will be able to displace the iron 3 plus from iron 3 oxide, giving us the molten iron and aluminium oxide. So the chemical reaction for this is Al solid plus Fe2O3 solid, giving us Al2O3 solid and molten iron. So why is aluminium able to displace iron from iron 3 oxide? Is because it is more reactive than iron. Question 4. We have three metals here, X, Y, Z. And based on the chemical reactions here, we are supposed to deduce what is the order of their reactivity. So let's take a look. X can displace metals Y and Z from their solution. So instantly we know that X will be on top, Y and Z will be below. So X is more reactive than Y and Z. Metal Z displaces metal Y from the solution of its compounds, but not metal X. So if metal Z can displace metal Y, we can say that metal Z is more reactive than metal Y. And here again it concludes that metal Z cannot displace metal X, so X must be above Z and Y. So place X, Y, Z in descending order of reactivity. Descending order means most reactive, the least reactive, and we have X, Z, Y. Right? X, Z, Y. So most reactive, least reactive. Because X can displace both Y and Z, Z can displace Y, but Z cannot displace X. Right? So if Z can displace Y, it means that Y cannot displace Z. Okay? Because in order for Z to displace the metal Y from the aqueous solution of its ions, Z must be above Y in the reactivity series. So we move on now to the thermal stability of some metal compounds. So why is this part important? Is because this part will actually lead on to the next section on the extraction of iron from its ore, or the extraction of any metal from its ore. So let's take a look at some simple metal compounds here. So metal carbonates. So potassium and sodium carbonate here are stable to heat. So what does this stable to heat means? It means that if I have Na2CO3 and I were to heat this, I will not get it breaking down into anything. Potassium, calcium, magnesium, aluminium here, for example, it breaks down into oxide and carbon dioxide. So for example, if I have calcium carbonate and I were to heat this really strongly, I will have calcium oxide plus carbon dioxide. Okay, so Based on its position in the reactivity series, it forms a compound which is less stable to thermal energy as it goes down the series. So imagine this. I have a very reactive metal, and this very reactive metal reacts with carbonate. So because it is so reactive, it means that the resulting carbonate is very stable. As you go down, it gets more and more unreactive. So if it were to react to form the carbonate, this carbonate compound wouldn't like to remain bonded to the metal. So we can say that as the as we go down the reactivity series, the metal carbonate becomes less and less stable to heating, or we can say it becomes less thermally stable. So thermally stable means less stable to heat. As we go down, right at the bottom, mercury, silver, gold, platinum, the carbonates formed are so unstable that they do not actually exist. So it spontaneously decomposes into the oxide and carbon dioxide. Or it doesn't react with carbon dioxide at all. It doesn't react to form the carbonate at all as well. So based on the reactivity of certain compounds, we will be able to determine what kind of substance it can react with. So if we take a look at the stability of metal oxides here, metal oxide. So for example, K2O. So K2O being formed from the reaction of potassium, a very reactive metal, with oxygen. If we heat it, there's no reaction. If we react with hydrogen, there's also no reaction. If we try it with carbon, there's also no reaction because it is so stable. So as we go down the series over here, you notice that all the way here, silver, mercury oxide, gold, platinum. So these compounds here, for example, silver oxide, when you heat it, it decomposes to metal and oxygen. But the next thing is the action of hydrogen on the metal oxides. So if we have zinc oxide, for example, plus H2, we will not get a reaction, no reaction. But as we drop one position down the series into iron oxide, iron 3 oxide, for example, it can be reduced to the metal by the action of hydrogen. So for example, if you have copper oxide plus hydrogen, we can get copper solid and water vapor. Okay, so copper oxide is reduced by hydrogen. It can be reduced by hydrogen, but it cannot be broken down by the action of heat. It cannot be broken down by the action of heat. So as we move across here, copper and carbon. Copper oxide can also be reduced by carbon to give you copper and carbon dioxide. So in this instance, when I use reduce, it means that the copper ion in copper oxide can be extracted out into the copper solid metal. So this is actually a very useful reaction for us to extract copper from copper oxide. So this leads us into the next section on how we extract iron from its ore. In this case, the iron ore is iron 3 oxide. So how do we make use of carbon or carbon related compounds to remove this Fe3 plus from Fe2O3 to give us Fe metal? So before we move on to the extraction of metals, this is the simple setup to show how we can use a gas to extract the metal from the metal oxide. So you pass hydrogen gas through, you heat the metal oxide, and if it can be reduced by hydrogen gas, at the end of the day we will have the metal here, and we have water vapor escaping from this tube over here. Okay, so for copper 2 oxide with carbon, as we mentioned in the earlier example, so we add these two together into a dish, we heat it really strongly, and after a while you will have your copper oxide reacting with carbon to give you your copper plus your carbon dioxide. So CO2 will escape into the atmosphere. Okay, you escape into the atmosphere. So what's left behind will be the copper metal, which is pink or reddish brown. Let's do a quick recap with checkpoint 2. So you can pause the video now to attempt the checkpoint. Continue the video once you are done. So question 1. Carbon will react with lead-2 oxide to give you lead and zinc oxide to give you zinc. So carbon can react with lead-2 oxide to give you lead and carbon can react with zinc oxide to give you zinc. Right, the chemical equation for the two reactions, very simple. It's something like this. You will get carbon dioxide being produced at the end of the reaction as well as the metal. So which of the oxides will be more easily reduced? So which one will react with carbon more readily? So if we think about the position of the metal in the reactivity series, we know that zinc is above lead. It means that zinc is more reactive than lead. So if it is more reactive, it forms an oxide which is more stable. So as a result, we can conclude that lead oxide would be the less stable oxide and hence it will be more readily reduced. Okay, so lead-2 oxide, because lead is lower down the series, so the lead-2 oxide is less stable than zinc oxide. Okay, so we conclude the stability of the compound by its position of the metal that is in the compound in the reactivity series. The more reactive the metal, the more stable the compound. The less reactive the metal, the less stable the compound. Which one of the following oxides cannot be reduced by both hydrogen gas and carbon to its metal? So this is actually in the table in one of the earlier slides. Let's take a look. It is actually this slide over here. So which one cannot be reduced by both hydrogen and carbon? Zinc oxide can be reduced by carbon. Lead oxide can be reduced by both carbon and hydrogen. Copper oxide can be reduced by both carbon and hydrogen, and we are left with calcium oxide here. So calcium oxide cannot be reduced by both hydrogen and carbon. So the answer is A. Option is answer number A. A. Moving on to question 3. This is a very interesting question. So you have the metal here, you have the metal oxide here in this glass tube, and this metal oxide is actually undergoing a reaction with the gas that is produced by the reaction between X and dilute hydrochloric acid. So you have HCl with X, it produces a gas, which allows the black colored metal oxide to turn pink. So if you think about this, the black color metal oxide, what could be the black color metal oxide? So recall earlier I said the black color metal oxide is most likely copper oxide, and it turning pink actually allows us to draw a conclusion that it is indeed copper oxide because the pink color metal would be copper metal. So which gas can reduce copper oxide into copper metal? It would be hydrogen gas. So how is hydrogen gas produced during the reaction between an acid and X? So if you think back, what is a possible reaction by which H2 gas is produced when you have an acid and something reaction? X must be a metal. So X must be a metal. So looking through this list of options here, we have Mg and Zn. So these two are metals. They react with the acid to give you hydrogen gas. And hydrogen gas will reduce the metal oxide here to give you the metal. And because it is a black colored metal oxide turning pink, we can conclude that it is copper oxide. Alright, the pink color substance is copper. The black color substance is copper oxide. And the metal is magnesium. So Mg plus HCl gives you MgCl2 plus H2. H2 is used to reduce CuO into Cu and H2O. A. Question 4 is a bit more tricky. You're supposed to look through these 4 equations here and deduce the reactivity of the metals. And you must arrange them in order as well, from the most reactive to the least reactive. So if we take a look here, how do we know which is the most reactive? How do we know which is the least reactive? Very simple. Let's look through the key parts of the equations. So if you observe the no reaction parts, no reaction means that the metal compound must be very unreactive because it doesn't react. The metal or the metal compound must be very unreactive. So we look through to see which one has the most number of no reactions. No reaction with water, no reaction with H2 and C, no reaction with water again, and no reaction with H2. So if something cannot react with water, if something cannot react with water, it actually means that the substance is very, very unreactive. Because most of the metals, if you recall, most of the metals can actually react with water. So only the metals that are lower in the series cannot react with water. So I can conclude that X and Z must be the two of the more unreactive metals. So which one is more unreactive? Is it X or is it Z? So very simply, if you look through, there are two no reactions here and there's only one no reaction here, which means that X is the least reactive metal. So X is the least reactive metal. So now we are supposed to analyze which is the most reactive metal. Based on the question here, actually, if you see X is the least reactive, the answer would be C already. But let's analyze the question a bit. So how do you know which is the most reactive metal? So let's take a look. Is it Y or is it Z? Which is more reactive? So if you can see that from this equation here, the metal oxide cannot be reduced by H2 or carbon into the metal. If it cannot be reduced by H2 or carbon, it means that the metal oxide is very stable. So in order for the metal oxide to be very stable, it must have formed from the reaction of a very reactive metal with oxygen. So the more reactive the metal, the more stable the product form. And because the product is very stable, it cannot be reduced by either H2 or carbon. So we can conclude that Y is the most reactive here. You see here, over here, the oxide can be reduced easily or readily by both H2 and carbon. It means that the oxide is not very stable. If the oxide is not very stable, it means that the metal used to form the oxide will be less reactive. So there we have it. We conclude that Y is the most reactive, X is the least reactive, so Z would be in the middle. And the answer is C. We now move on to the second last part of this topic, which is on the extraction of metal. So this part actually builds on the previous part on the reactivities of the metal oxides with carbon and hydrogen. So the picture you see here is actually a quarry where iron ore is mined. The trucks here are huge. The wheels of the truck here, if you can see this wheel here, it looks tiny, but in fact, if a man were to stand here, the man would only be able to reach this level of the truck. So imagine how huge is this truck. So a lot of iron ore is mined daily. Why? Because we use a lot of iron in our daily lives. If you take a look around you, almost everything you see is made of or contains some iron. Your stainless steel contains iron. Your foundation beams of buildings contains iron. The phone that you're using, I'm pretty sure contains some iron parts. The spoon you're using, stainless steel contains iron. The roof, look up above you, the roof is probably held in place by iron support beams. So iron is a very widely used metal, and as a result, a large amount of iron extraction is taking place around the world. So how is the iron obtained from the iron ore? How is it obtained from the iron ore? This is a picture of a iron refining plant. We will cover more on this later. So the method of extraction of the metal depends on its position in the reactivity series. So if you recall earlier, if I have potassium and I have gold, gold is so unreactive that in nature it exists by itself. So to extract the gold, it's very simple. We just have to dig it out from the ground, and we get the gold already. But if I were to extract potassium, because potassium is so reactive, in nature we will find it reacted with something else. So how do we extract this metal from the ore? It depends on the position in the reactivity series. And we use two main methods. One is electrolytic reduction, and one is the reduction with a substance, for example carbon in this case. So for the more reactive metals here, as you can see, they are found bound to something else in nature. So when you dig out, for example, you dig out sodium, you will find it as sodium chloride. So how do we obtain sodium from sodium chloride? We use electrolytic reduction. This will be covered more on the topic of electrolysis. NaCl is decomposed by electricity to give you Na plus Cl2. So this is obtained through electrolytic reduction. The less reactive metal compounds here, can be extracted by reduction with either carbon or hydrogen. So, for example, if we want to obtain, say, mercury from HGS, mercury sulfide, or cinnabar, we can reduce HGS with carbon in the furnace, and we will get the mercury metal. So, based on the position in the series, the ease of extraction changes, with the ones at the top being the hardest to extract and the ones at the bottom being the easiest because they are found unbound in the ground. So we move on to the extraction of iron. So first things first, where is iron found in nature? When you dig the ground, you do not find iron as Fe free by itself. If you always find it bound with something else, and in nature, iron is most commonly found in hematite, iron 3 oxide, or Fe2O3. And because you dig it up from the ground, there's sand, there's clay, and there's a lot of other impurities. So these are some iron 3 oxide hematite lumps. You would commonly see these lumps in shops selling crystals. They would profess that these lumps have some healing or some magical properties and ask you to hang it around your neck, hang it around your arms, and so on and so forth. So these are actually hematite lumps, Fe2O3, iron 3 oxide. So how do we extract the iron from the iron 3 oxide? So first of all, we need this huge device called a blast furnace. The blast furnace technology has in fact not changed much since it was first discovered long time ago, about a couple of hundred years ago. So mankind discovered how to extract iron from iron 3 oxide by adding various substances, and the method has remained largely unchanged, except that the scale has gone up through the roof. So this is a blast furnace. It can be tens of stories tall. And into this blast furnace, we add the substances iron ore, which is Fe2O3. We add coke, which is carbon, and we add limestone, which is calcium carbonate. And we pump it full of preheated air. Pump it full of preheated air to warm up the whole reaction vessel here. This is actually a huge reaction vessel. So once the reaction is warmed up, it proceeds. The reaction progresses, and we get the iron. So let's go into the individual equations which allow us to produce the iron in the blast furnace. So step 1, coke or carbon. It reacts with oxygen from the air, from the preheated air that is pumped in at the bottom to form carbon dioxide. This reaction is extremely exothermic, and because it is exothermic, it releases a lot of heat, and the temperatures here can reach about 1900 degrees. So carbon plus oxygen gives me carbon dioxide. And because there is so much coke present in the blast furnace, the carbon dioxide that is formed can react with more coke to give carbon monoxide. This reaction is slightly endothermic, and because of this, it absorbs temperature from the surroundings, and the temperature will drop to about 1100 degrees Celsius, which is still mightily high. So what is installed for the carbon monoxide? This is the key equation for the extraction of iron from iron 3 oxide. So the carbon monoxide here reduces iron 3 oxide into iron and carbon dioxide. So Fe here is Fe3 plus. Over here is Fe0. So Fe3 plus to 0 plus 3 to 0 is a reduction. So this is a reduction step. So stage 3 is actually the reduction of Fe2O3 into Fe. And because the molten iron is less dense, because the molten iron is the densest, it actually flows downwards and collects at the bottom of the blast furnace. So if you recall the earlier diagram, you have something like this. This is the molten iron, and this is what we call slag. Later on we'll go more into what is slag. So the molten iron will flow downwards. It will flow downwards, and it will collect right at the bottom of the furnace, and we can just pipe it out and we can have our iron. But as I mentioned earlier, hematite is not found by itself alone. When you dig it up from the ground, you will find it with sand, with clay, and with many other impurities. So how do we remove these impurities from the whole reaction mixture? So recall earlier we added limestone in. So limestone, calcium carbonate, is not thermally stable. So when you heat calcium carbonate, we can get calcium oxide and carbon dioxide. And this calcium oxide can be used to react with some substances. So if you recall, calcium oxide is a metal oxide. So being a metal oxide, it is a basic oxide. Sand is actually silicon dioxide. And silicon dioxide is an acidic oxide. So if I have a basic oxide and I have an acidic oxide, I get a simple acid-base reaction to give me the substance, which in this case we call slag. So calcium oxide reacts with silicon dioxide to give me CaSiO3 or slag. We call this Casio cube. Casio with a cube. So molten slag. So slag is less dense than molten iron. It floats on top of the molten iron. Take note, this is slag and this is molten iron. So the slag actually plays a role in the blast furnace. Notice that it is above the iron, so it prevents the iron below from undergoing further reaction with the oxygen, because if it is iron, it can react oxygen to give you iron 3 oxide, right? But why doesn't this reaction take place? Because there is no oxygen in contact with the iron. Why? Because the slag forms a layer above the iron and it seals away the part of the entry of preheated air which contains the oxygen. Okay? And during the reaction, you get many waste gases produced. You get carbon monoxide, you get carbon dioxide. So all these hot gases escape from the top of the furnace. Right? They escape from the top of the furnace. So let's attempt checkpoint 3. Pause the video now to attempt the checkpoint. Continue the video. Now let's try checkpoint 3. So the iron ore used in the blast furnace contains impurities such as silicon and sulfur. So how do we remove them? Silicon is removed as slag by reacting with calcium oxide. Silicon is found in the form of silicon dioxide, SiO2. So how is sulfur removed? And explain why its removal is detrimental for the environment. So sulfur is found by itself as sulfur. So how is sulfur removed from a blast furnace? If you think about this, in the blast furnace, what conditions are present? There's high temperatures, there is a lot of preheated air which contains a lot of oxygen, and this means that the sulfur can react with the oxygen in the air to form, yes, that's right, form sulfur dioxide. So the sulfur burns in the presence of oxygen to form sulfur dioxide, and with this, when SO2 is released into the atmosphere, it can dissolve in rainwater to give you acid rain. So SO2 plus water gives you sulfurous acid first, sulfurous acid, and this is further oxidized by oxygen in air to give you sulfuric acid. So this is what gives us acid rain. So the blast furnace is lined with refractory bricks made from aluminium oxide, Al2O3. So explain why Al2O3 is used. Why don't we use something like plastic? Why don't we use something like aluminium? Simply because in the blast furnace, if you recall, temperatures can reach up to 1900 degrees Celsius. It is really high. So we need something with a very high melting point like aluminium oxide. So why is aluminium oxide's boiling point or melting point very high? It's because you need a large amount of energy to overcome the strong electrostatic forces of attraction between the aluminium and oxide ions. So strong forces, a lot of energy required. It means that it has a very high melting point and it can withstand the high temperatures in the blast furnace, which can be up to 1900 degrees Celsius. Now let's move on to the products that are produced from the blast furnace and what do we use? What do we do further? What do we do next with the substances that is formed? So First of all, the iron that is produced from the blast furnace is what we call pig iron. It is really impure, it's pretty impure, it contains about 4% carbon. There's too much carbon inside already. So if you recall, when you have another substance within a metal lattice structure, it disrupts the structure. It disrupts the structure. So normally it's like this. If you have too much impurities, this is how your metal will look like. Too much impurities. The metal structure is now disrupted. If it is disrupted to too large an extent, it actually breaks down because you can't really form very strong forces of attraction between the cation ions and the delocalized valence electrons. So, in order for us to use the iron that comes from a blast furnace, it must first be purified. So, how do we purify this? It's very simple. Carbon can be easily burned off by blasting it with oxygen gas. So we pump oxygen gas into the pig iron. So by pumping in hot oxygen gas, it reacts with the carbon to give us carbon dioxide, and carbon dioxide escapes into the surroundings and it is lost. So at the same time, sulfur that is present in the iron also burns to give you sulfur dioxide, and this escapes. Phosphorus in the iron is now converted into phosphorus oxide. Silicon is converted into silicon dioxide. So all this, they can react with your calcium oxide, which is a basic oxide. This is an acidic oxide. This is an acidic oxide. So you can react with your calcium oxide to give you slag and other substances. So if you recall, the calcium oxide is formed from the decomposition of limestone. CaCO3 to give you CaO plus CO2. And CaO plus SiO2 gives you CaSiO3, which is also known as slag. So what do we do next with the iron that is formed? So we can do various things. If we add in about 0.25% carbon, we get mild steel. If we add in tungsten, we get tungsten steel. If we add in chromium and nickel, we get stainless steel. So all the different kinds of products that is formed from the iron is used to make various items, and these items here have different substances added in because they need to have different properties. For example, to make drills, you must have a alloy which is really strong. So we add in manganese, and we get increased strength and hardness to make your drill, because you wouldn't want your drill to be blunt after you drill an object, and you have to keep resharpening it. So now let's move on to checkpoint 4. Pause the video now to attempt the checkpoint. Continue with the video once you are done. Checkpoint 4 is a pretty easy checkpoint. So question number 1, how does alloying increase the hardness and strength of the iron? So if you recall, iron is a metal, giant metallic lattice, cations and a sea of delocalized valence electrons. They form layers. So when we add in other substances, they disrupt the orderly arrangement. They disrupt the orderly arrangement of the original parent metal. And because of this, they don't allow the layers to slide easily. The layers cannot slide easily when a force is applied, and as a result, the hardness and the strength increases. So different size atoms disrupt the regular orderly arrangement, and the layers cannot slide. As a result, it becomes more hard and stronger. Question number 2. So while alloying can increase the strength of the iron, if we add in too much substances, it can actually make the iron brittle. So it's the same. So imagine you have a lump of clay. So as you knead the clay, as you knead the clay, as more and more dust and dirt is kneaded into the clay, eventually the clay will start to break out into small little tiny bits. Correct? So this is the same for alloying. As you add more and more other foreign particles, your original structure can no longer hold. So the integrity of the structure is lost. So as a result, because the integrity of the structure is lost, the resulting alloy becomes extremely brittle. So a small force is applied, the layers slide, and then they break apart because the metallic bonds can no longer hold the atoms together. Okay, so you add too much already. It disrupts the structure to too great an extent. So when the layers slide, the metallic bonds can no longer hold the cations together, and as a result, the iron block shatters. We now move on to the last part of metals, which is on rusting. So rusting is a term which is most commonly misused. So have you ever looked around and you've seen metal objects with a layer of some weird substance which looks like a powder, and you say, aha, this is rust. Aha, that is rust. So you see a block of copper and there's dirt on it and there's something which looks like rust to you, and you say, aha, the copper is rusted. Actually, this is a wrong way of using rust, because rust can only be used for the first question: which of the following iron sheets will be least likely to rust? So let's take a look. You have something coated with zinc, which is more reactive metal than iron, so it will be preferentially oxidized. Coated with a layer of grease. This is just barrier protection, excludes your water and oxygen. Your water and oxygen excludes both water and oxygen. Coat with a layer of copper on the side. Copper is a metal which is less reactive than iron. So in fact, if you coat iron with copper, if the copper is scratched, the iron in fact will rust even faster. You coat something in waterproof paint and there's a scratch below, so there's no use, because if there's a scratch, the iron is exposed to water and oxygen and it will rust. So answer would be A. The iron is coated with zinc. Zinc is more reactive than iron. So in the event that there's a scratch, the zinc will be preferentially oxidized over iron, and it protects the underlying iron. So answer is A. In which setup will the iron nail not rust after 1 week? So if you recall again, to rust you need iron, you need water, you need oxygen. So you must have all these three compounds, all these three substances present. So if we take a look at the first one, we have a thin layer of oil on top of the tap water. Tap water contains both O2 and H2O, so it can still rust. In this case, there's no protection at all. We have O2, we have H2O, and we have more O2 dissolving from the atmosphere, so this can still rust. In this case, we have boiled water. We have boiled water here. So boiled water actually removes the oxygen, so no oxygen, but we have water present and we have iron present, and this is exposed to the atmosphere, so oxygen can dissolve. So eventually we will still have oxygen in, we will still have water, so this can still rust. So for option B, it's boiled water again. So boiled water means that there's no oxygen, there's no air, so no oxygen in the water. There's water present, there's iron present, but the thin layer of oil on top prevents the oxygen from air from dissolving into the water. So no oxygen present. Even if you have water and you have iron, you can't rust. So the answer is B. Alright, the last part of this notes actually covers the social, economic, and environmental issues of recycling metals, as well as why certain metals should be recycled, certain metals shouldn't be recycled. Take a look through them. You may be asked to comment on these issues in your questions, especially in the database questions. You may be required to read data from the tables and then interpret why some metals are not recycled. For example, why is iron not recycled versus gold? Why is gold recycled? So other than this, if you have any queries, any doubts, please relook through the lectures, look through the worked examples in particular. So we have come to the end of the lesson. Thank you very much, and I'll see you in the next lecture series.